said, okay, it is actually give you very peculiar characteristics, okay, because very small amount of boron, okay, will actually increase hardenability to a higher end. And also boron is not hardened, no, very in large extent, because boron is actually not good. Okay, instead, you add more and more boron, it is not good because it will form some kind of carbide. Okay, there is also more formation of carbides like B4C. In more boron, if you add, it can form B4C. Okay, here, here, all these kind of carbides. Okay, these carbides are very brittle. Will make the steel brittle. Clear? Because the hardness will be so much increasing, the steel will be brittle. Okay? So that's why boron is not added to a large extent. Huh? Only some few, in like almost somewhere in ppm level also it is added. ppm level. Okay. So you can see this. Okay. So as the austenite grain size becomes finer, the hardenability effect of boron increases. Okay? Like if you more austenite grain boundary, if it's more austenite grain boundaries are there, then boron can easily go on the grain boundaries. Okay, so effect of boron will be more, so more chances of martensite formation. Clear? And hardenability will increase. Clear? So this is one case, and there is also like austenitizing at high temperature reduces the hardenability effect of boron. Like if you increase the temperature, boron effect will be reducing. Okay, right? So how it is actually reducing? For example, if you see here, like in this temperature range, you can see the solubility of boron in austenite, okay, is very low. Clear? For example, at about 912 degrees Celsius, okay, it is only 0.001 weight percent, okay, and it is increasing within temperature to a maximum value of about 0.005 weight percent at the UTEC. That means what? If you remember, this is eutectic temperature A1. Okay. This is A4. Eutectic. This is eutectic temperature. Again, this is eutectic temperature. So this here it talks about this temperature 910 degrees Celsius. Okay. Clear. So at 910 degrees Celsius, this maximum solubility will be how much? 0.01%. Now, as the temperature will increase, the solubility will maximum increase. Okay. Up to from 0.001 weight% to 0.0005 weight%. So which is actually very low actually. Okay. There is no significant increase here, but the temperature effect you can see. Okay, temperature effect. So from 910 degrees Celsius, it can go up to eutectic temperature, which is around 1150 degrees Celsius. Okay. Clear? So the high temperature increase, this effect will be good actually. Okay, clear? The boron will increase the percentage of its content, right? Solubility. But there is a problem, like if you come to the lower temperature range, like alpha iron. Okay, so in alpha iron, the solubility is essentially zero, okay, almost. Okay, right? Because this is a BCC structure, so boron will not go into the BCC. Okay? It will maximum chances go to the FCC. And it is influenced by the impurities present because of its low solubility in austenite. Boron can be highly concentrated in grain boundaries. Okay, so more chances that will go to grain boundary. So when you go to grain boundary, it will form that there will be this boron carbide formation. Okay, clear? So this boron carbide formation, what it will do? It will actually retard the formation of, because this is actually a covalent carbide. Okay, this carbide is a covalent carbide. Clear? This covalent carbide will actually what? Retard the formation of pearlite and ferrite. Clear? If it could be incoherent, then there is more chances of formation of pearlite and ferrite. Clear? So as this is a covalent carbide, so it will promote the formation of martensite. Clear? So in that way, you will see that, okay. In that way, you will see that the because of the covalency, you will see that the boron will actually increase the hardenability of steel by delaying the formation of ferrite and pearlite at the grain boundary. Clear? And by promoting the formation of martensite. Clear? How it happens? As the it is covalent, if this carbide is covalent and austenite actually, okay, there is a already covalent. This is covalent carbide, and there are alternate grains are there, right? Lattice. So as the covalence is there, what will happen? That will result in a reduction in surface tension. Means surface energy will reduce, and also grain boundary energy will be reduced. If grain boundary energy is reducing, then there is no chance of the formation of colloid and ferrite. और थोड़ा high grain boundary energy रहेगा तो chances of nucleation of colloid and ferrite will be easy. Okay, clear? So in that way, actually what will happen? It will form a structure which is actually more suitable. That is nothing but martensite. It will form martensite at the grain boundary. Clear? So in that way, boron has its effect. Okay, and so this boron has this effect of boron is given by a term called boron factor. Okay, so this boron factor is given by this BF. Okay, B subscript F. So which is given by the diameter. Okay, the ratio of the ideal diameter from the Grossman method. Okay, ratio of the ideal diameter with boron upon ratio of the ideal diameter without boron. Clear? So with boron, whatever the diameter is that, okay, and if you divide that with the diameter without boron, then you will get the boron factor. Clear? And the boron factor is actually represented by like this. Okay, boron factor versus boron percentage. Okay, you can see this is 0.002 boron. So you can see the boron effect. Okay, the boron factor is maximum when it is about 0.003 or 0.002%. Clear? Later on, what happens as the percentage of boron will increase, it decreases. Okay, this is effect. Clear? That's why boron effect is actually less. Okay? Like if you increase the percentage of boron, it will not affect so much. Okay. Only there is a limit. So maximum you can go maximum 0.005% you can go maximum. So show this effect. Clear? This range. So you can see this. Okay. Boron contents about 0.03 weight% lead to a loss in hardenability. Na? Clear? This boron factor will decrease the hardenability factor. Okay, clear? So that's why boron in excess about 0.004%. Boron causes a loss in toughness to precipitation of boron iron boride. Okay, in austenite grain bound. Okay, clear? This different borides will be forming. Okay, even boron carbide will form. Okay, even borides will form. Like tungsten boride will form. Okay, tungsten is there. Okay, so that's why you will see that you don't add boron. Okay, maximum. You can add maximum 0.001. Remember. This is suitable. Clear? This is suitable amount. Generally in ppm level it is added. Okay. Okay, so this is about the boron effect.